Hi everyone. In this video, we are going to look at combination. uh, Two objectives. First, we want to know the definition of the combination, especially we want to differentiate between combination and permutation. And secondly, we want to use this formula. Actually, we use a calculator to calculate combinations. First, let's look at the definition. What is a combination? Combination, like in permutation, is also a arrangement where no items can be used more than once. This is the same as in permutation. And the most important part is that this is how you differentiate between a combination problem and a permutation problem. The order in which these selected items are being selected makes no difference. Then that means order doesn't matter. For example, if we select 3 students from a class to represent that class to attend a meeting, let's say the 3 selected students are called A, B, C, A, B, and C, 3 people. And do you think the order in which these 3 people are selected makes any difference in terms of representing this class to attend that meeting? It really doesn't make any difference because no matter who is selected first, second, A being first, B second, C third versus B being the first, A being the second, and C being the third makes no difference. It's still same 3 people representing the same class, attending the same meeting. What's the difference then? There's no difference. Until or unless these 3 selected people or students, they play different roles or they take different positions. Until that, it makes no difference. So whenever it is no difference, as long as the order in which this selected item being selected makes no difference, it is called a combination. So this is some kind of comparison between combination and permutation. Permutation problems involve situations in which order matters. Combination problems involve situations in which the order of items makes no difference. That's key difference between these two. That's how you determine which formula to use. So far, all of 3 methods to do counting are presented to you. The first one is called fundamental counting principle. The second one is permutation. This is the third one. We call it combination. Now, let's look at an example. And this basically a practice problem to identify whether we have a permutation permutation problems or a combination problem. For each of the following problems, determine whether the problem is one involving permutations or combinations. It is not necessary to solve them. So it's not about answer the questions. It's about identifying whether we have permutation problem or a combination problem. A, 6 students are running for government, student government president, vice president, and treasurer. The student with the greatest number of votes becomes a president. The second highest vote getter becomes a vice president, and the student who gets the third largest number of votes will be the treasurer. How many different outcomes are possible for these 3 positions? First of all, this is a counting problem because it asks us how many possible outcomes. Secondly, you need to consider what kind of situation we have. Should we use fundamental counting principle? Should we use permutation? Should we use combination? That's a question you always ask when you have a counting problem. And this particular one is a permutation problem. First, we select 3 people out of 6 student body, right? We select a certain number out of another certain number, and that is either permutation or combination. It depends on whether this this order in which this three selected people make different or not. In this case, it makes difference because this three selected people take different positions. That's a key make a difference. Like the example we mentioned in the previous video, Biden being the president versus Harris being the president makes huge difference, even though that's the same two people taking the two top positions, right? Order makes difference. So this one is a permutation. Now let's look at the other one, the next one. We have three of this in total. So B, 6 people are on the board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. So they need to select 3 people to form a committee. How many different committees could be formed from the 6 people? Again, we select 3 people out of 6 people. So whenever this happens, you either have a permutation problem or combination problem, depend on whether the order in which the 3 people selected makes difference or not. In this case, it makes no difference. The reason is very simple. Nowhere they mention these 3 people assume different roles or fill in different positions. As a result, the order in which these 3 people are selected makes no difference. So this is a combination problem. Now, the last one. Baskin Robbins offers 31 different flavors of ice cream. One of its items is a bowl consisting of 3 scoops of ice creams, basic ice cream bowl, each a different flavor. All of the ice cream bowls, each one of them consists of 3 different flavor ice cream in it. How many such bowls are possible? So basically, and we have 31 different flavors. This is essentially ask us how many 3 different flavor ice cream bowl possible. In other words, to form this ice cream bowls, we need to select 3 flavors at a time, right? Now, we select 3 out of 31. So either we are going to have a combination problem or we have a permutation problem. Which one is the right one? It depends on the order in which you put these 3 flavors in the bowl makes difference or not. To me, I guess I believe actually to most majority people, order in which these 3 flavors are put in the bowl makes no difference. For example, if I want 3 flavors such as banana, strawberry, let's say chocolate, just for the sake of example, I want these 3 flavors. I don't really care in what order these 3 flavors of ice cream are put in the bowl. As long as I get the same 3 flavors, I'm fine, right? So order makes difference. Order makes no difference. That's what I meant. So this is the combination problem. Okay, let's move on. This is just for the purpose being able to tell whether we have a combination problem or permutation problem. Next, we're going to develop this combination formula, even though you don't use the formula directly to do any calculation. This will help you to be able to differentiate the 2 formulas between combination and permutation. Now, let's look at this statement. We have seen that notation NPR means the number of permutations where you select R items out of N items. That will give you how many different ways to select R item out of N items. One order makes difference in which those R items are selected. Similarly, the notion that NCR apparently will select R items out of N items, where the order in which these R items are selected makes no difference. So that's just a different symbol. We use combination when order makes no difference. Now let's look at this example. Consider the letters A, B, C, D. The number of permutations of these 4 letters takes 3 at a time is, in other words, how many different ways to take 3 letters out of these 4 letters, how many outcome possible. So since order matters, because we're talking about a permutation, we select 3 out of 4 letters, and order matters. If we do that calculation, that's 24. If we do this calculation, it will be 24. That means there are 24 unique outcomes if we select 3 letters out of 4 letters where order makes difference. See, I have this empty space. I'm going to show you literally those 24 different outcomes. Based on this, we're going to develop our combination formula. Remember, this one currently is a permutation. So we have A, B, C, D, 4 letters. We select 3 out of 4. Now I'm going to write down all of these 24 different ones. So first, suppose I select A, B, C. And ACB is not the one. Remember, order makes difference. This are considered to be 2 different outcomes. So I have 6 now. There's 6 different ways to select ABC actually. Order makes difference. Now let's do others. If we select B first, so another 6. So we have 24 different outcomes, exact 24, number no less. This one order makes difference in which these 3 letters are selected. Now imagine if order makes no difference. In that case, we will call it combination, right? Say if order doesn't matter. So what's the outcome then? So we still select 3 letters out of 4. So how many outcomes we have? All of these are considered to be the same outcome because order doesn't make difference. In this case, I just say, hey, I just select ABC. That's only one outcome. So this become one outcome. All of this become one outcome. You can write ABC, whatever you write, it just says 3 letters because order doesn't matter. Just as long as you write 3 letters, that's the same outcome. We just have one outcome. Similarly, this one, we just have a BAD. That's one outcome. They're all the same. Order makes no difference. This one is ACD, and this one is BCD. We have 4 outcomes. 24 become 4. Much fewer outcomes if order doesn't make any difference. So the thing is, here's a critical part. When we select 3 out of 4, each column has 6 outcomes because if you rearrange these 3 letters, one order makes difference. When you rearrange these 3 letters, it has 6 different outcomes. And how do we get 6? Because order matters. We arrange this among these selected 3 letters. That's 3 out of 3. We select 3 out of 3 to arrange them. And if we do calculation, and this is 6. This is 6. 3. Select 3 out of 3. Now this is C. Let's redo that. Should be P. 3. Select 3. That's 6 different ones. And this one is also equal to 3 factorial. Whenever you select n out of n, it is equivalent to equal to n factorial. So if you do 3 factorial, which is 3 times 2 times 1 is also 6. So this is the same thing. Now, when you select 3 letters out of 4, each 3 letter has 6 combinations. All of the 6 combinations become 1. One order makes no difference, right? We understand that now. Now imagine if we didn't do this select 3 letters out of 4 letters, we select 4 letters out of 5 letters, then that's a 4-letter rearrangement among themselves will produce more than 6. That's a 4 factorial. 4 factorial is 24. That means each column going to have 24. One order matters for 4 letters. What if order doesn't matter? That 24 outcome also become 1. So in other words, when order doesn't matter, no matter how many different ways you arrange these select ones, that column will become 1, always become 1 outcome, because one order makes no difference. That's the same letters. So always become 1. Now here's a critical question. When I select 3 out of 4, each column has 6, and that 6 has to become 1 outcome. But if I select 4 out of 5, each column is going to have 24 different arrangement. All of the 24 will become 1. Now, if we do this individually, we understand that. But if we want to formulate a formula, that's a little trouble, because no matter how many different arrangement in a single column, you always become 1. How can you make different number all become 1 in the formula? Because one order makes no difference, no matter how many, they all become 1. There's only one way to do that. Just divide by whatever in this column by itself. If there's 6, divided by 6. If there's 24, divided by 24. If 50, divided by 50. Any number divided by itself is 1. So in other words, we just divide by how many are in here, which is given by factorial. If we select 3 letters, 3 factorial. If select 4 letters, 4 factorial. Divided by that. What divided by that? We use the original one. This is if this 6 means this is order matters, right? That's a permutation result. We use a permutation result divided by a factorial of the numbers of selected items. That will give us combination result. And look at this formula. This formula is combination formula. What's the difference compared this to the permutation formula? This is a permutation formula. We learned this in the last class, last video. N minus R factorial. What's the difference? Only difference is this. Look at that. This is a permutation formula. Like I said, the result of a combination is using the result of permutation divided by the factorial of the selected item. Selected item is represented by R, divided by another R factorial. This formula divided by another R factorial. Whenever you divide by anything, you put that thing on the bottom, right? That's why we put R factorial in here. It becomes this. So this is a select R items out of n items where order makes no difference. That's a combination. That's the only difference, but the difference is huge. Like this one, 6 become 1. The whole thing 24 become 4. Okay, now this time, let's say redo the example. Yeah, so we already know that we select 3 letters out of 4. Select 3 letters out of 4 where order makes no difference. Where order makes difference, we know the answer is 24. That's what we did. Select 4, select 3. Out of 4, this equals 24. Now let's do this using the combination where order makes no difference. We still select 3 out of 4. And let's use either formula or calculator, doesn't matter. If I use a formula, n is 4, so 4 factorial divided by n minus r factorial, 4 minus 3 factorial, and divided by another r factorial. So we do the calculation. This is 4 times 3 times 2 times 1. You don't have to do the calculation using calculator. This can cancel most of it. 1 factorial times 3 factorial, which is 3 times 2 times 1. 1 factorial just one time, just 1. Basically 1 times itself. And you get 4. Using calculator, that's a beautiful part using calculator. No matter how big the number, we do it in one step. 4, we select 3 out of 4. Order makes no difference. That's combination. The result is 4. But understanding what situation you have is more important than this calculation, because calculation part is the easiest part. Now let's look at another one. How many 3-person committees could be formed from 8 people? Again, we just form a 3-people committees. We just select 3 people out of 8 people. They didn't mention these 3 people play different roles, assume different positions, right? So order doesn't matter in which these 3 people are selected. So select 3 out of 8, order doesn't matter. That's all it takes. And select NCR 3. There are 56 different ways to select the 3 people out of 8 people. In other words, there's 56 possible different committees. Each committee is different from another committee. So we already did it using calculator. We already show you how to use the formula, so we don't need to redo this part. Now let's look at the next example. This is the pure calculation problem. You can do the first one on the top, write down the numbers, and then this one, write the number and do division, or you can do this whole thing as in one step. I'm gonna do it twice to show you both. So let's do each individual one. Select 3 out of 10. Always input n. Select 3 out of 10. We get 120. Then select 4 out of 6. This should be 15. Let's try that. Select 4 out of 6. Yeah, 15. 120 divided by 15 is 8. So the answer is 8. In other words, the number on the top is 8 times as much as the number on the bottom. Just like 10 divided by 2 equals 5. Everybody can interpret that, right? This means there are 5 2's in 10, or you can say 10 is 5 times as big as 2. This number is 8 times as big as this number. Now let's do it in one step. Select 3 out of 10. There's a 0 in the front. Let's redo that. Select 3 out of 10. And divided by select 4 out of 6. Yeah, that's all it takes. Equals 8. So you can do it in one step. Now let's look at another example. The key to solving all of this, to answer all of these questions, is that you identify what counting method you need to use. Fundamental counting principle, combination, or permutation. So let's look at this. A professor gives his students 9 essay questions to practice in preparation for an exam. Only 4 of those questions will actually appear on the exam. How many different exams are possible? That means how many ways to select those 4 questions are possible, because each 4 questions give you an exam, right? So basically, we have a situation where we need to select 4 out of 9. So this just tell you either have combination problem or permutation problem, but which one is the right one depend on if the order in which these four questions are selected matters or not. Apparently it doesn't matter, and it doesn't matter to 99% of people, because for the same four essay questions, if I am the student, I said student, I don't really care because I get exact same students. I don't care in which order they appear on the test. It really doesn't matter to me. It's just the same four questions. So order makes no difference. Whenever we say order makes difference or not, it refers to the selected items, not the whole candidates items. So select 4 out of 9, order makes no difference. Let's see how many different tests are possible. Select 4 out of 9, 126. The professor can create 126 different 4 essay exams. I do know a person in my personal life that there's a test consists of 4 questions, and she gets right all of the 4 questions. What questions are on the test before the test, day before the test? That's just unbelievable. From this, you can see the chance is very low to guess right all of the questions. Now, this is another one. In poker, a person is dealt 5 cards from a standard 5-card deck, and the order in which the 5 cards are received does not matter. Apparently, that's common sense. Imagine if you are that poker player, does it really matter to you in what order those 5 cards are dealt to you? To me, absolutely not, because I got the same 5 cards. Who cares in which order they gave me? In the end, I got the same hand. So how many different 5-card poker hands are possible? In other words, they just ask you how many ways to select 5 cards out of 52 cards. Even though they deal that to you, but it's like select 5 cards. Randomly, you select 5 cards from that 52 card deck. So we select 5 out of 52, and order doesn't matter. The key is that order doesn't matter. Yeah, NCR. Look at that number. Let me copy it. 259,8,960. What is that? Little bit more than 2.5 million different 5-card hands. Imagine a poker player and a lot of calculation in his or her head. There's more than 2.5 million different 5-card hands. Now let's look at another one. To win a lotto in the state of Florida, one must correctly select 6 numbers from a collection of 53 numbers, 1 through 53. In other words, pick 6 numbers out of 53 numbers. The order in which the selection is made does not matter. Again, we are told order doesn't matter among the 6 numbers. In other words, as long as you have the exact same numbers, no matter the order, you win. How many different selections are possible? That means how many unique tickets are possible. When you have same numbers, that's why in this situation, there could be several people or even many more people win the same prize because they have same numbers, even though order are different, they have same numbers, they all win. So we don't care about that. We just care about the mathematical part. So basically, we select 6 numbers out of 53. Order doesn't matter. If order matters, there's many million different result, different tickets. That's why sometimes in a huge payout Powerball lottery, when there's no price when and there's more people buy, right? They say, oh, the chance is 1 out of 330 million, something like that. That's why order matters. You have huge number of possible tickets. Only one is the final winner. So select 6 out of 53. Order doesn't matter. So we have, let's write down 2295748 Let's see, what is this? It's almost 23 million, almost. See, order doesn't matter, still this many. You know, when order matters, the number many times higher. Just like those 24, when order matters, when we select 3 letters out of 4, we have 24 different results. But when order doesn't matter, there's only 4 left. So when order matters, this number is going to become way, way bigger. Okay, we just have a few more, 3 more actually. The first one, this one is kind of similar to one of your homework questions. In December 2011, the US Senate consisted of 51 Democrats and 47 Republicans and 2 independents. How many distinct 5-person committees can be formed if each committee must have 3 Democrats and 2 Republicans? So if without the last requirement, it's just another combination problem. We just select 5 people out of 100 people to form committee, right? But there's a specific requirement. This 5-person committee must consist of 3 Democrats and 2 Republicans. Otherwise, it's not a valid one according to this rule. So how do we do this kind of counting problem with the restrictions? First, we need 5 people out of 100 people. That's for sure. Let me write down the basic information here. We have 51 Democrats and 47 Republicans and 2 independents. And we want to have 5 people. And this 5 people is not any 5 people. It has to be 3 Democrats and 2 Republicans to be called a valid committee, because that's kind of a rule in this particular question. Now, if you go ahead and select 5 out of 100, we know when we select committees, select people to form committees, order doesn't matter as long as those selected ones don't assume different roles, right? So we do have a combination problem. But if you do a combination like this, 5 out of 100, that will be totally wrong. The reason is that this way assume we randomly select 5 people out of 100 people, so that everybody get equal chance to be selected. In that case, there's no way you can guarantee this selected 5 people are going to have this kind of structure that is required. You could have all 5 Democrats, that's absolutely possible, or all 5 Republicans, or any other combinations. As long as it's not this kind of structure, it's invalid. Why you do a lot of selections that are invalid in the first place? Think about that. So in order to guarantee this structure, which is the only valid structure in this case, we only select these 3 people to guarantee they are Democrats out of 51 Democrats. So guarantee it will be valid. We only select the other 2 people are supposed to be a Republican out of Republican group. Then this way, any committee we formed is a valid one. So in other words, we just cover all of those possible valid committees. That means we get all of them. And actually, this is 2 counting rules combined into one problem. Each time you select this 3 Democrats out of 51, or you select the 2 Republicans out of 47, that's a combination problem. We already know that. Select a number of people from another group of people, and order doesn't make difference, that's combination. But since this whole thing is take 2 steps, we select 3 Democrats first to see how many ways to do that. Then we select 2 Republicans to see how many ways to do that. And how many ways to do this whole thing, we multiply them together. That's fundamental counting principle. It involves 2-step procedure. So let's do that. We select 3 Democrats out of 51 Democrats, and then we select 2 Republicans out of 47 Republicans. Then we multiply them together. That's how many different ways to have this 5-person committee, or that's how many 5-person different 5-person committee possible. So let's do that. Select 3 out of 51. Well, that's a big number. We don't have to write it down. That's times. Select 2 out of 47. Yeah. Certainly this is a big number. I expect a big number. 1, 1, 8, 2, 5. That's more than 22 million different committees. More than 22 million different committees. Okay, move on to the next one. How many different committees can be formed from 5 professors and 15 students? If each committee is made up of 2 professors and 10 students, what's the difference, fundamental difference between this one and the example we just did? No difference, 100% similar. So you have some restrictions, right? Let's say how many professors to be available, 5 of them. So 5 professors and 15 students. This is our candidate pool. What we want? We want committees that is made up of 2 professors, 10 students. We need 2 professors, 10 students. This is like Democrats, Republican. We need this many Democrats, we need this many Republicans, right? Exactly the same thing. So let's go ahead and do the calculation. We select 2 professors out of 5. Oh, that doesn't make difference because they didn't mention what role these 2 people are going to play. And times, we select 10 out of 15 among students. So we just do this in one step. 2 out of 15. Oh, 2 out of 5. Sorry about that. That should be 10. 2 out of 5. Yeah, that's 10. Times, we select 10 out of 15. No way we can. I can do that in my head for this one. This one is big. And select 10 out of 15. Yeah, 3003. So when you multiply by 10, just add 0 at the end. So we have a little bit more than 30,000 different committees. Last one, cards again. Oh, this one is now everybody pay attention to this one. This one is similar, I guess, similar to your homework problem. I remember I pulled this one out of your homework pool. So you may not see this one, but you see similar kind of problem. 5 cards are randomly selected from a standard deck of playing cards. How many hands contain exactly 2 queens and 2 kings? Don't forget you need 5 cards. This only 2. This only 4 cards. You need 5. So it goes like this. And pretty much this is a restriction on your selected cards. Even though you have 5 cards, it's not that we select 5 cards out of 52 cards. How many different ways to do that? If that is the case, we just see using C combination 5 out of 52, and that's it. But there's restrictions on these 5 cards, just like there's restrictions on these committees. So we need to take the same approach. In order to get the exact 2 queen, we can only select these 2 cards out of all the queen cards. To get 2 kings, we only select the 2 kings out of king cards to make sure this structure is right. That's the way to do this kind of problem. So next question is, how many queens are available in the deck of cards? So that's a common knowledge, right? We have 4 of each, 4 kings, 4 queens, and 4 aces, and 4. Everything is 4 ones, 4 twos, right? So we have 4 queens available. We have 4 kings available, and this time we want to have two queens. This is what we need, okay? From this group, and we need 2 from this group. We also need 1 more because we need 5 cards from the rest. And the most challenging part for this problem, oh, no, sorry about that, is this part, the rest, because this rest cannot contain any queens, any kings. Because if you still have that, so the one you select happen to be that, you will destroy this structure that you already finished. You have to have exactly 2 kings and 2 queens. As a result, the rest cannot have any kings, any kings in it before you select this one. How do we do that? Remove these cards from the deck, totally 8 of them. So 52 minus 8, 52 minus 8, that's only 44 cards left. Make sure you select this one from this 44. Now each selection is combination because we know when you play poker, this order in which you receive those cards makes no difference. So we select 2 out of 4. We select 2 out of 4. We select 1 out of 44. Now multiply them together according to fundamental counting principle. And each one is 6. I'm going to use a calculator to show you. And this is 6, and this is 44. So we just multiply them together. So let's use a calculator to show this select 2 out of 4 is 6. Right, 6. So 6 times 6 times 44 times another 6 times 44. So 1,584 different 5 cards hands that contain exactly 2 queens, 2 kings, and another card, and a different card. And that's all for this video. See you guys in the next one.